The purpose of this lab is to predict and compare motion between the two falling objects using Newton's second law. The result was that both fell at the same rate with some very slight discrepancies towards the end of the free fall due to an insignificant amount of drag force. In this lab, using Newton's second law, we will first compute the force of gravity on both the objects as it is acting on them in the system, which is equal to the negative mass of each object, mass of the object times the gravitational constant of the Earth, which is 9.8 meters per second squared. And we're going to assume that the net force acting on it, or the only force acting on it, is force of gravity because the drag force is so minuscule in this experiment. And we will use Newton's second law to get the final velocity by computing the previous velocity and adding that to the net force of the object over the mass times delta t, and then we will get the new position by having that equal to the previous position plus the velocity just found times delta t. Here's the code that I have for the lab. For my two objects, I use a ball and a shoe, which I have created here. And the shoe, for the model, I just created a sphere, made it black, and made it bigger to represent that it's bigger and has a bigger mass. Here I instantiated the mass of the ball and the mass of the shoe, and the weight of the shoe is approximately, just a bit over, twice over the weight of the ball. And the position vectors, I started the ball position at negative 0.5 on the x and the shoe at 0.5 on the x. Just for display purposes, as we're not observing the x and the y, as we're not observing the changes in x, so I just put them, so they're easier to see for the model. And the ball's position for the y direction is I was able to get at negative 0.004, and the shoe position was able to get at 0. Delta t is a 0.033, which is the frame rate that I use in tracker, and we have g, the gravitational constant, to be 9.8, and j hat vector, which will be the direction of the force, which is in the y direction. Here we have the time to be 0.6, less than 0.6, as that is how long the time was in tracker for the objects to fall. And I could use the calculations that I talked about previously. We're getting the weight of the ball, the force of gravity of the ball, by getting the negative ball times gravity times the j hat, which will give us the direction. We have that equal to the net force. And I did that the same for the shoe. And we used the equations before to get the ball velocity, the new shoe velocity, and the new ball position, and the new shoe position. And after running this, you will see that the two objects are falling roughly at the same, actually no, they're falling at the same rate, and you see they stop at the same spot. And you can see clearly that the weight force is a lot bigger for the shoe than that of the ball. This is because just the mass of the shoe is greater, so the weight force would be greater, but the acceleration of both objects remain the same, so they fall at the same rate still. Here's a graph of the two objects falling at the same rate. As you can see, they're pretty identical. You see the ball's position is the blue dots, where the position of the shoe is the red line. Now here's my experimental position versus time, where you can see the ball still the blue dots, the line, and the shoe is the red. And as you can see, as it starts getting later on in the duration of the free fall, the shoe begins to slightly, just very slightly, lag behind a bit. And this is due to the drag force, and I'll explain why it affects the shoe more in just a moment. What if these objects fell for a longer period of time? Well, the effect of drag force would become more apparent, making the shoe lag a bit noticeably behind the ball. The equation for the drag force will help you to show you why this is. The equation of the drag force is equal to the P, which is the air resistance, times velocity squared of the object, times the cross-sectional area of the object, and times the coefficient of drag force. In this case, since they're both not the same type, as in the ball is a sphere, like, and the shoe is, just like a flat end shoe, the coefficient of drag is going to be different. but not enough to really have that much of an impact. What really creates the big impact between the shoe and the ball, which is why we don't really need to compute it as it is apparent, is the cross-sectional area. The cross-sectional area of the shoe, the bottom of the shoe, the sole, is that's a lot greater cross-sectional area than that of the ball, thus making the drag force a lot greater and affecting the ball a lot more. Now, what does this mean? This means that in most cases, when comparing objects of different masses, they tend to fall close to the same rate if the duration of free fall is lesser. If the duration were relatively longer, the discrepancy with drag force would no longer be as insignificant, noticeably increasing the distance between the objects during free fall. Thank you.